All right, in this video we're going to talk a little bit about electrical resistance. Now the thing to know is that anything hooked up to a circuit, anything that you're trying to get electricity to flow through has some resistance. Things that are good conductors have a really low resistance. Things that are poor conductors would have a really high resistance. But even conductors themselves have different resistances based upon some different factors. Now, one of the things that can affect how well a conductor conducts or how much resistance it has is the material. So, for example, use of most metals, particularly like copper. Actually, really good conductors are gold and silver. But we don't put those in the pipes in our house because they would be worth more if you tried to sell them as opposed to trying to use them to transmit electricity, even though they would real well. But copper is a little more affordable, so we use copper as a really good conductor. It has low resistance. Whereas things that are more insulators, like glass, plastic, air is an insulator. Remember, lightning only strikes when it actually can separate the electrons and kind of ionize the air so that the current could pass through. Otherwise, it's a very good insulator. These things you would never connect to your circuit, right? You wouldn't use plastic wires to send electricity to a light in your room or in your house because it wouldn't do anything. It doesn't conduct. It has a high resistance, which actually makes it really good for coating the wires, right? If you notice, if you ever look at the wires we use in class, even like the wire right here on my computer, if I stick it on there, there's a metal conductor through in the middle of this wire, but it's coated in a rubber, a polymer plastic that's a good insulator. So it contains that electrical charge inside the conductor so that it gets from the outlet to your computer and goes nowhere else. So that makes it have a really high resistance. The other thing we can do to affect resistance is change the thickness of the conductor, right? So if I have, say, a number 2 gauge wire, which is a thick wire, versus like a number 16 gauge wire, which is a thin wire, I'm going to be able to get more current to flow through the thick wire. There's more free electrons available to push the current through. With something really small and thin, I got less material available to actually carry the current through, so this is going to have a lower resistance. And I can get more current. Whereas a small wire will have a higher resistance. I'm going to get less current. Now, one of the ways you can see this, if you go to your house and you look outside where the power comes into your house, it's probably some thicker wires than you see actually going to the outlets in your house. Because the thicker wires coming into your house is going to need to carry all the electricity needed for the whole house, whereas the little wires only need to take it out to individual devices. So you can only use so much electrical energy out of each outlet. So thickness has an effect too. Another thing is temperature. One thing you'll notice as we're doing labs is when you have electricity flowing, it causes the objects that it flows through to produce heat. Right? They heat up. And think of it this way. If I have a wire, all those electrons are constantly bumping and colliding into one another, right? And as they collide, they move around and they jostle each other, right? And as things move around, they heat up. Okay? And so the more they heat up, the more they kind of knock into each other and actually kind of make it harder for electricity to flow. So if you were to leave a circuit on for a really long time, those wires would heat up, those components would heat up, and they wouldn't conduct electricity as well. They would become, as the heat goes up, the resistance goes up. That's one of the reasons why I'll tell you, when you have your components in your circuit, turn them off and shut them down when you're not actually trying to measure something, because they will heat up over time, and that affects the way they operate. It increases their resistance, which makes it harder to push the electrical current through it. And then the last thing we'll say is length. The length of a circuit affects resistance. So a longer run has more resistance. And if you think about it, the electricity needs to pass through a longer section of wire. So as the length of the run increases, it's going to take more and more energy to push that colliding group of electrons through from one side to another. One way you can think of this is like, think of a straw, right? If you have a really long straw and you're trying to suck a big thick milkshake through it, it's going to be harder, right? If you have a short straw, there's a farther distance that you need to move that material, move that milkshake. It's going to be a little easier to suck out. Now, one way you can think of this is your connection at home to your DSL or to your TV from your antenna. If you have an antenna on the roof and you have a TV in your bedroom upstairs where it's a really short run, you should get a pretty good clear picture. But if you have a really long cable run all the way to your basement, you might get a little static. Now, in the days of cable, there's amplifiers along the way to kind of boost the signal strength, so you might not notice that on your cable TV. But if you were to set up an old-fashioned antenna, you would definitely be able to see that. You get a worse signal when the longer wire run. So that means there's more resistance in the line.